This is Power Generation Controls by Graham Brawley, Gloria Bryan, Clara Larsen, and Austin Simon. Maintaining the proper frequency of a power grid may be important than you know. Take, for example, the continental European power system, which supplies power across 25 different countries. In March of 2018, international conflict between Serbia and Kosovo brought Serbia to bring some of their power plants offline, which destabilized the entire grid by dropping continental European power generation 113 gigawatt hours below its required level. This net generation shortage continued for months, with the European grid's average frequency being below its nominal frequency of 50 Hz. Over time, this frequency error caused clocks that derive their time from the frequency of the mains power grid to run slow. After months of frequency error, mains clocks ran as much as 6 minutes slow, causing real issues for affected people and industries. This case demonstrates the importance of controlling the power grid's frequency by proper feedback control of its generation plants.
The inputs to our system are the generator mechanical power, PM, and the disturbance, PL, which is the power drawn by the loads. The output signal that's being optimized is the electrical grid frequency. Since these are all per unit variables, the reasonable values for PM, PL, and omega are between 0 and 1. The variable H represents the ratio of kinetic energy of the generators to the rated power of the generators. The variable D represents the natural system damping due to generator damping loads, which are frequency dependent. Both of those constraints are essentially physical properties of the machine and are subject to change with different systems and generators. Reasonable values for H are between 4 and 10, and the reasonable values for D are between 0 and 5. The transfer function for this system is shown on the screen, with frequency over mechanical power equaling 1 over 2 times H times S plus D. The transfer function for the load is similar, here shown as omega of S over P of S equals negative 1 over 2H times S plus D. We can then use this function to further analyze the system's stability.
After evaluating the poles and zeros of the transfer function, the open loop plant is BIBO stable by itself. This is mathematically confirmed by the open loop transfer function having a pole at negative 1/8 with H equals 4 and D equals 1. The open loop system is modeled with the load power being modeled by step functions. Now, the reason we can use step functions is that our system will almost exclusively receive step inputs from load powers. Every device that is added to or removed from the power grid will be a disturbance to the system, and most of these devices that come online will always have instantaneous power requirements that go from 0 when the device is off to their max power consumption in a small amount of time. These disturbances can therefore be modeled as step inputs to the system. As far as the specifics of the operating system, the plant has a rise time of 17.22 seconds and a settling time of 19 seconds when evaluated with a kinetic to electric power ratio, H, value of 4 and a natural damping value, D, of 1. The plant responds quickly with this settling time and maintains the requested output frequency, giving our assumed step inputs.
Using Simulink, we built the block diagram shown here. As can be seen, there are two inputs to the system, PM, which is the mechanical generator power, and PL, which is the system disturbance due to the power drawn by the loads. We modeled the mechanical power as a constant frequency because the generator will always be operating at its rated nominal frequency of 1 PU. According to industry standards, the generation frequency is allowed to vary from the desired frequency for a total of 24 hours every quarter of a year. This results in a settling time of less than 40 seconds. It is also preferred that the steady-state error and rise time are as small as possible, with the hope that the steady-state error is exactly 0. To achieve this, a PI controller was used, which ensures that the steady-state error is minimized. The value of Kp for our PI controller is 0.539, and the value of Ki is 1. The closed-loop transfer functions are shown here. One of these is related to the mechanical generator power PM, and the other is related to the disturbance from the loads PL. Utilizing the root locus plot for the PM transfer function, it can be shown that the system is stable for all k, making it an extremely robust system. On the graph, this is verified by the fact that none of the poles or zeros cross into the right-hand plane.
The output of the closed loop system is shown on screen. As is shown, the rise time is 1.053 seconds, the settling time is 7.22 seconds, and the final value is 1 pu. This final value means that the steady state error is 0. The percent overshoot is 18.5%, which is much higher than the industry standard from the NERC 3-1.1 of 5%.
According to the Bode plot for our system, the gain margin is infinite, and the phase margin is 66.8 degrees at a crossover frequency of 1.28 radians per second. According to these values, the maximum time delay before the closed loop system becomes unstable is 0.9108 seconds.
In conclusion, we met two of the standards set by the NREC for stability. With this control system, we are able to ensure that the system is within our settled frequency with 32.78 seconds less than the time the system was allowed to be off frequency and still be within the highest level of standard compliance. We were also extremely accurate with our system after every disturbance, and because of this we are within the 5% error margin that the frequency is given. The only standard we did not meet was our overshoot, which was about 4 times what the standards wanted. Overall, the closed-loop control system is effective at controlling the grid frequency within NREC standards.